Hi there guys, welcome to this video where we're going to take a look at another problem from a sixth term examination paper. And in this particular video we're going to be taking a look at the 2020 step 2 paper, and it's question 1 that we're going to be taking a look at. So just a word of warning before we start. The step papers changed a little bit around, I can't remember the exact year, 2018, 2019, something like that. So there used to be 3 step papers, step 1, 2, and 3, that concentrated on, the first 2 concentrated on the normal A-level mathematics content, and the third paper concentrated much more on the further mathematics content. Things changed, and now there's just 2 step papers, step 2 and step 3. Step 1 was phased out. We're just left with step 2 and step 3. Step 2 concentrates on the normal A-level mathematics material and the AS further mathematics. Step 3 is the whole of it incorporates all of further mathematics, or potentially all of the contents of the further mathematics A-level course. So if you are looking through past papers and using them to as preparation for your step exam, do be aware of that, because it did actually catch me out. For the third part of the question that we're going to be looking at today, it turns out you need some techniques from further mathematics really to solve it. And I'd kind of forgotten that things had changed. So I saw step 2 and I was still thinking, oh, it's just the normal A-level math stuff that we're using out. And I wasn't getting anywhere with the problem. So just be aware that things have changed. Nevertheless, the older past paper, the older step papers prior to the change are still well worth looking at. Okay, so if you are preparing for a step paper, in my opinion, you can go all the way back to the beginning. So there's some that you can download that go back to the late 80s. And I've even included, I've got some videos on my channel going through some problems from the really early step papers from the late 80s. They're still relevant in the sense that they're still good practice. Maybe some of the specification material has changed over the years naturally, but nevertheless they're still excellent preparation for you, so well worth a look at. Okay, so let's have a look at the problem that we're faced with. So this is an integration problem. I'll include the problem somewhere on the screen, and also I will include a link in the description to this video so that you can download this particular past paper and any other past papers that you want to take a look at. So let's have a look. Using the substitution x equals 1 over 1 minus u, where 0 is less than u is less than 1, yada yada yada, to find in terms of x the integral 1 over x to the power of 3 halves. Is it x minus 1 or 1 minus x minus 1? X minus 1 to the power of a half dx. Okay, and that's for x is greater than 1. Okay, so it's an indefinite integral that we need to do, integration by substitution. So hopefully you're familiar with integration by substitution. If you're not, then make yourself familiar with integration by substitution. And as is usual with step problems, the first part is kind of gently just easing you into the problem. So much so that in this case, we're actually told which substitution to use. Okay, there's still a bit of work for us to do, but it's nice and easy. Okay, so what have we got? We've got x to the power of 3 halves, sorry, is going to be equal to 1 over 1 minus u to the power of 3 halves. Also, the first part of step problems are often establishing some sort of pattern that is maybe built on in the next part of the problem, and then in the final part you're kind of expected to have seen what the pattern is and abstracted that problem, that pattern, and that you're able then to take it further completely on your own in the third part. That's not always how it works, That's a very common kind of theme. So you're introduced to something, you kind of guide it through it. The next stage is you give them less guidance, but you build on that idea, and then finally off you go. You're on your own. Okay. So x minus 1 is equal to 1 over 1 minus u minus 1, which is 1 minus u. So that's going to be u over 1 minus u. So therefore x minus 1 to the half is u over 1 minus u to the half. So I call this I just because I'm lazy and I can't be bothered writing it out all the time. So we get the integral of 1 over x to the power of 3 halves. So that's going to be 1 over 1 minus u to the power of 3 halves times u to the half. So square root of u, 1 minus u to the half. I need to differentiate. So dx by du is equal to 1 minus u to the power of minus 2. 1 over 1 minus u squared du. So we get some interesting cancelling here. And we're left with the integral of u to the power of minus a half, which is 2u to the half plus c. Don't forget your constant of integration. What I find with a lot of A-level students is that the constant of integration becomes kind of an afterthought, particularly when you're first introduced to integration. Its significance is not really made clear to you. Some people get it, but a lot of the time it's just something that people know that they need to include to get their marks on the exams, but they don't really understand what it is, how it works and things like that. And this can lead them into all sorts of difficulties, particularly when it comes to solving differential equations by separation of the variables, maybe, where the constant of integration, if it's not inserted at the right time, then it can end up in the wrong place. Okay, so that sometimes when you do some integration, you solve these differential equations, the constant of integration is not just plus c on the end of your expression. It's actually somewhere else inside your expression. So what can happen is that people will integrate, they'll forget about the concept of integration. They'll kind of rearrange to get their expression into a suitable form as described in their exam problem. And then right at the end, they'll remember the concept of integration and they'll just kind of slap it on the end. And it's in completely the wrong place. And it now makes that solution to that differential equation completely incorrect. Okay. So when does your concept of integration go in? It needs to go in as soon as you've integrated. Okay, it's actually not going to make too much difference here, but just a word of warning. Make it habitual as much as possible that you include the concept of integration as soon as you've integrated when it's an indefinite integral. So what do we get here? We get 2. I need to rearrange this to make u the subject. So we get 1 minus u equals 1 over x. So u is equal to x minus 1 over x. Twice x minus 1 over x to the power of a half plus c. Okay, and that's it. Okay, that's the first part done. Now, what you could do at this stage, and what I recommend that you do at this stage, is that you actually check this. And I'm not talking about here being in the exam. I'm talking about when you're preparing for your STEP exams and you're going through problems from past papers and things like that, take the time to check your answers. Don't just turn to the answers, the mark scheme or whatever, and check it, because you're denying yourself certain opportunities there to further develop your knowledge and understanding. By checking this, you're getting extra practice with well, in this case, you check it by differentiation, right? Differentiate this and make sure you get back to this. You get extra practice at differentiation techniques, okay? You you start to get a better understanding, a much deeper understanding of the relationships between differentiation and integration. You'll start to see various patterns emerging, which you don't necessarily need to consciously try to remember, but somewhere in the back of your minds, all of this stuff, it kind of accumulates to your benefit. If you constantly deny yourself these opportunities, you're really going to slow down your progress. You're not going to be getting as much bang for your buck with the time that you're putting into your studies. Because really, you've got limited time. You need to make the most of it. Okay? And one way that you can make the most of it is by figuring out ways to check your own answers and actually checking them. And in this way, you'll also build up your confidence. If you're constantly checking your answer against some external source, mark schemes, back of the textbook, whatever, you're developing a certain habit there, which is not necessarily good for you, and it doesn't do any good for your confidence, because you never really get to a stage where you feel that you're in charge, that you know what's going on. It's almost like you're just doing things, and sometimes you do the right thing, sometimes you don't, but you don't really know when. You constantly need somebody or something to tell you when you're doing things right, and this is not good. This is not good when it comes to trying to solve challenging problems in mathematics, because you need to be in charge of what you're doing. Okay, so I did check this through differentiation. It does work. So I'd be happy with that. And even in the exam, would I check this? I would have done. So do you have to check your answer? No. Should you check your answer? You decide. Okay. It depends on your level of confidence. If you get to your answer and you're absolutely 100% confident that what you've got is the right answer, then there's no point in checking. If you're honestly 100% confident, then a check is it can't make you any more confident than you already are. If you're about 80% confident, maybe you think that something could have gone wrong in here, you are human after all, we all are, then maybe it's worth just checking it. It might show up that something's wrong, in which case you can find out what's wrong, and it might be something that you can quickly put right. And just taking those few seconds to check this, which is just a simple differentiation calculation, might actually save you from losing out on a certain number of marks. Okay? So, let's move on to the next part. And let's see what we get up to with this part. Here we go. So it's another indefinite integral, and in this case it is, let me get it right, x minus 2 to the 3 halves times, what was it, x plus 1 to the half dx. Okay, so in this case, when x is greater than 2, not that we really care, to be honest with you, but just to be clear. Right, so in this case, we're building on the idea from the previous part, but we're not given quite as much guidance here, okay? Notice that the form of the integral is very similar in many respects to the form of the integral from part 1. This kind of corresponds to the x to the 3 halves, this bit of the previous integral. This corresponds in a way to the x minus 1 to the half. So the powers kind of match up. So if you observe this might be useful. This might give you some indication about what might be worth trying. Not always. But here we're expected to find our own substitution. That's on the understanding that it is actually integration by substitution that we need to be using, which I think it is. I think that's the idea that we're building on here. I can't see how integration by parts is going to be useful here. So, but try it. I haven't actually tried it. Maybe try it yourself. Try integration by parts, see if you can get anywhere with it. So don't necessarily feel that you should look at this and know what the substitution is straight away that you need to use. That's not how it works. Maybe for normal A-level maths, when you do integration by substitution, and in the cases where you're not given a substitution, my advice usually to my students is, who are not doing step and things like that, is choose the obvious substitution to make. Now, initially, when you first start doing integration by substitution, that's a bit wishy-washy. You know, what do you mean by that? Because it's not obvious at that stage. But once you've got a bit of experience with integration by substitution, once you've seen a few cases, once you've done a few yourself, if you've been paying attention, you'll start to notice the pattern, okay? And they become very predictable in your normal textbook, A-level maths textbook kind of problems. But on step, it's a little bit more difficult, okay? Even when you need to use integration by substitution, I can't just necessarily say, choose the obvious substitution, because the substitutions are often far from obvious. And that's the case here. But we've been given a bit of an idea about where we need to go, potentially, what ideas we need to build on from the first part. At least that's the hint that we're getting, at least. So, because I noticed that the powers kind of matched up here, I didn't just dive straight into really complicated substitutions. I actually made two separate substitutions. The first one was really just to bring this into a form that was similar to the first part of this problem. I didn't expect this first substitution that I made to be the substitution that I needed to use. That wasn't the intention behind it. I was using it purely as a kind of intermediate substitution, something to facilitate things. Okay, so the substitution that I made, and I made this fairly early on actually, was x minus 2, u equals x minus 2. So in that case, we get x plus 1 is going to be equal to u plus 3. du by dx is equal to 1, so we get dx is equal to du. And therefore, this becomes 1 over u to the power of 3 halves, u plus 3 to the power of a half du. Okay, so you can see how it's much more closely resembling the integral from the first part, but there's still substantial difference, right? So this corresponds to kind of the x to the power of 3 halves. This corresponds to the x minus 1, but obviously I don't have u minus 1 here. So I could, by the way, at this stage, change these u's back to x's, because it's just a dummy variable at this stage. But I'm going to leave it as u. Okay, so now that I've got things into a very similar form to the first part, this is where I started to look for maybe a substitution that was more along the lines of the kind of substitution that we saw in the first part. So you could do worse at this stage than just actually trying out the substitution from the first part. If you're coming up blank with any ideas, just give it a try, okay? It might be a bit naive, it might not work, but by trying it out, you might actually give yourself some hint as to where to go. Now, I didn't actually try the substitution given in the first part of this problem. I had other ideas that I wanted to try out, although I did use that as motivation, the substitution from the first part. But there was a bit of trial and error, and be prepared to do this when it comes to solving problems. Be prepared to try things out, do a bit of trial and error. So it's not just random poking around here, there, and everywhere. It's okay. Maybe the first thing that you try is kind of random in some ways, but still there's going to be some motivation behind it. Try to observe what works, what doesn't work. The stuff that works, can you keep that in somehow? And the stuff that doesn't work, how is it not working? And is there a way that you can modify it so that it does work? Okay, and that's kind of the principle that I was working on here. So the initial substitution I made was u equals, what was it? 1 over t minus 3. Okay, u equals 1 over t minus 3. Why was this? Well, previously, in the previous part, we had this, in part 1, we had the substitution u equals 1 over, sorry, it was x, wasn't it? X equals 1 over 1 minus u. So remember, we had x minus 1. So I was thinking, okay, because it's kind of x plus 3 here, maybe that changes the signs around a little bit, and maybe the 3 here needs to be, that means we need a 3 here, and things like this. Okay, I was trying to construct a pattern. Now, initially, this is going to be a very naive attempt. Okay, you're really clutching at straws, and I was fully aware of this, and that's how it's got to be sometimes. You're clutching at straws, but you feel that there's something worth pursuing. Okay, so I wasn't expecting this to work. It doesn't work. But what I was hoping for, which did happen, is that this would kind of point me in the right direction, maybe. Again, I'm looking at what works, what doesn't work. Can I keep the stuff that works? Can I get rid of the stuff that doesn't work? Kind of idea. Okay, so when I did this, I got u plus 3 is equal to 1 plus 3t minus 9 over t minus 3, which is equal to 3t minus 8 over t minus 3. And the word that I would use to describe this expression is fussy. Okay, that was one of the first words that came to mind. It looks too fussy. And if I substitute this in here, I'm going to get an expression that's going to be too fussy to integrate. I don't like it. But then what don't I like? I don't like in the numerator here, I've got kind of two terms. I've got the 3t and I've got the minus 8. What I'm wanting is kind of a single term. Okay, maybe just a constant, or maybe something just involving t. So if I'd had, for example, here, just 3t over t minus 3, I would have been kind of happy with that. Or if I just had minus 8 over t minus 3, I would have been kind of happy with that. So my attention kind of turns to that now. Can I construct a substitution such that when I calculate u plus 3, I get something here that's less fussy? And yes, these are the terms that I'm thinking in, so these are not very precise terms necessarily, but they make sense to me in the moment in my mind. Okay, it understands that ideas don't necessarily come to you when you're trying to solve a problem. They don't necessarily come to you in a logical way. And it's very difficult sometimes to really articulate to someone exactly what it is that motivates the particular idea. Now, in these videos, that's what I'm trying to do. I'm trying to do that difficult job, but it's not always possible, because sometimes there isn't a clear motivation why I decided to do something, either why I decided to do this or that, and not the seemingly obvious thing over here. So I will try to articulate that as best I can when I can, but sometimes there's just times when I can't. There's something that just sparks in your mind, something, a light bulb just switches on, and you have to seize the moment. Okay, you've got this idea, don't let it get away from you, just seize it. Try it, either it works or it doesn't work. But what you find is that very often it does work, and it's very mysterious how this works, why it is that you just get these random ideas and they just happen to work. But maybe it's suggesting that there's something deep down in your subconscious mind that's just churning away, and it's doing a lot more work than you necessarily realize. And it's a big part of problem solving is really developing your intuition. This is why it's so important, well before any exams, that you get plenty of practice at solving challenging problems, because This intuition takes a long time to develop to a satisfactory level, and it never stops. The further you go, the greater the level of intuition you have to develop. So researchers in mathematics will have a much higher level of intuition than I do, for example. But it is a process that you've got to go through, and it is a skill that you've got to develop, and you've got to learn to listen to those intuitions. This is not something that can happen the week before an exam, and it doesn't suffice for you to just know on a surface level how to do integration by substitution, for example. You've got to have seen integration by substitution in all sorts of different contexts. Simple contexts, much more difficult contexts, and everything in between. So that you've got a chance to develop an intuition of trying things out, seeing what works, seeing what doesn't work, so that your brain somehow registers this information, and it's much more prepared. The further into this process that you go, it's much more prepared to generate ideas for you subconsciously and just give them to you. Okay. And it just takes a long time for this to happen. It's not something that you can force. It's not something that all you can do is encourage it. Encourage it by actually solving problems and going through the hard work, by the way, and not just whenever you arrive at a difficulty in a problem, just going to the answer. Okay, it's not the answer that you need. It's the process, the journey through the solution to the problem. Actually going through that journey, which is frustrating. It's humbling sometimes. It's torturous. You can feel the whole range of emotions in the solution to a single problem sometimes, but you have to go through it because you have to develop those mental strategies that you need in order to solve mathematical problems. And there's no guarantees. Don't misunderstand me. There's no guarantees at the end of it. But the more you do this, the better you become at problem solving. Okay, so what I ended up doing was, just by kind of fiddling around with this a little bit, I knew that a 3 needed to be in there, obviously. I ended up with u equals 3 over t minus 1, was it? Yeah, 3 over t minus 1. Because then when I calculate u plus 3, what do I get? I get 3 plus 3t minus 3 over t minus 1, which is 3t over t minus 1, which is less fussy. Okay, much less fussy than this thing. So I knew when I saw this that I didn't really want to pursue this idea, this particular substitution, if I could help it. But once I saw this, I thought this is something that's worth pursuing. Now, at this stage, I've still no idea whether this substitution is actually going to work. Understand this, that sometimes you don't know until you try. You don't know until you know. So all I've got at this stage is just a gut feeling that this is on the right tracks. You know, this is simple enough. And also, if you remember from the first part, when we had the substitution x equals 1 over 1 minus u, for example, when I calculated x minus 1, what did we end up with? We ended up with u over 1 minus u. This was also something else that I was basing my idea on, that in the first part, this worked. There's the kind of template of the pattern that I need. Now I'm building on it. Okay, this is what I was kind of getting at. You're given an idea. It's not necessarily clear what the idea is, or what you're supposed to be drawn towards. Sometimes you don't know until you know, and sometimes you don't even consciously realize. You just pick up on certain things, and you know that that's kind of what you need to build on. And once I got to this point, I had a feeling that this was the right kind of thing that I needed. Okay, so what happened then? So we've got I is therefore equal to the integral of 1 over So it's going to be 3 root 3 t minus 1 to the power of 3 halves times u plus 3 to the half. So it's going to be square root of 3 t to the half t minus 1 to the half. Differentiate this, we're going to get minus 3 over t minus 1 squared dt. Okay, as before, we get loads of cancelling. This 3 will cancel with this 3. Don't forget about the minus sign though, we are going to need that. And we get minus 1 over square root of 3 times square root of 3 is 3. Integral, t minus a half. T to the power of minus a half. How nice is that? So that's a nice thing to integrate. It's just going to be minus 2/3 t to the power of a half plus c. Again, don't forget your concept of integration. So that's minus 2/3. I need to rearrange this to make t the subject. So we get t minus 1 equals 3 over u. So t equals 3 plus u over u. Over u to the power of a half plus c. We're not done yet because that was only one of the substitutions that I made. Now I need to resubstitute in to get my integral in terms of x. So 3 plus u is going to be x plus 1 over u, which is x minus 2 to the power of a half plus c. Bingo. Okay, we're done. I checked this, it does work. Again, do you have to check? No. Should you check? It's up to you. Okay. My advice is to check whether you're in the exam or whether you're not in the exam. Just do a check. Right? It's a bit of differentiation. If you can't cope with a bit of differentiation, okay, you've got problems. Right. So that's my solution to this bit. And I just want to emphasize that the solutions that I give to problems in these videos, they're not meant to be model solutions. What I'm trying to do is to really articulate the problem-solving process. Okay? If you're wanting model solutions to these step problems, all I can say is watch other videos, because this is not it. The reason that I want to focus on problem solving and the problem solving process is because I think it's something that so many people have difficulty with. Because a lot of videos kind of go through, they give model solutions and they tell you what to do to solve a problem, but not necessarily how those ideas were generated in the first place. And this is the most difficult part of problem solving, is actually generating ideas and getting on the right track. It's easy to be just told, do this, do that, do the other, especially if you're familiar with the techniques that are involved, but actually putting those techniques together in that original way yourself in the first place is a very difficult thing to do. So that's what I'm trying to do in this, is to, in these videos, is really to try to get across what is it that motivates me to do things. And as I already said, this is sometimes very difficult to do because there isn't a clear motivation. But as much as possible, when those motivations are there, are clear to me, then I want to try to get them across so that you can see what kind of things I'm looking at, what kind of things I'm noticing in a problem, what's motivating me to do the various things that I do. So let's move on to part 3. And this is where things get a bit more fun. Okay. So what we're dealing with now is the integral from 2 to infinity. So we're dealing with a definite integral here, as opposed to an indefinite integral that we have been dealing with. 1 over x minus 1 times x minus 2 to the power of a half times 3x minus 2 to the power of a half dx. Okay. Righty-ho. So I had some real difficulties with this, first and foremost because I'd completely overlooked the fact that the step exams had changed around this time. So I I saw step 2 and I was still thinking in terms of how step 2 used to be. I'd forgotten that there had been that change, because I do skip around the different step exam papers in these videos. So sometimes I'm doing step papers from maybe a year or so ago, or maybe from 10 years ago, maybe even 30 years ago in some cases. So I completely overlooked the fact that there was the potential for some further mathematics techniques to be involved in this. So I spent quite a significant amount of time trying to solve this just using normal maths techniques. Don't do this, because you will waste a lot of time. Once the penny dropped, though, once it dawned on me that you could start to use further maths techniques, then it opened up new possibilities. Of course, I still had to find the right solution, but I still had a lot of work to do. So I'm going to go through some of the difficulties that I had, even knowing that I could use further maths techniques and so on and so forth. It's still important for me to show how certain ideas that I had that didn't work motivated my ultimate solution to this problem. Okay, so notice that there is the form of this integral is kind of different to the form of the integrals that we've had in the previous 2 parts. Okay, note we've got 3 terms kind of in the denominator here, if you want to call them terms, and the powers are different as well. Okay, so I tried all sorts of things here. I tried to bring this into a similar kind of form in some ways, maybe by expressing it as a sum of 2 different integrands, both of which maybe maybe one of which has kind of a similar form to what we had in part 2 or part 1, and another integrand that would be a bit more straightforward to integrate. Maybe it would be the same form as that in part 2 or part 1, but maybe not. Okay. Other things that I noticed. Here we've got x minus 2 in the denominator, and here we've got 2 as the lower limit of this integrand. Now that's interesting to me, because if you were to just give me this expression, I don't know what the graph of this function looks like. Okay, I've not put it into any graphing software, but if I were to look at the graph of this, I would expect there to be a singularity, or a vertical asymptote, should I say, at x equals 2. Okay, which is quite interesting from the perspective of an integral, because it's just, an integration around asymptotes is generally not straightforward. But that led me to believe that maybe I need to do something with that. Maybe I could get that out of the denominator in some way. I don't know how, but it's just something that I've noticed. But also, I've missed something off. We need to show that this is equal to pi by 3, of course. Something else that I noticed based on what I see here is that we've got pi. How's that? Where does that come from, right? That to me can only come from, really, in this context, some kind of trigonometric function appearing in here. So it's either going to be a trigonometric substitution that I need to make, and bearing in mind that I've got infinity here, it's probably not going to be sine or cos, but it could be inverse. So it could be cosec or sec, or it could be the inverse functions. Hint, hint. But I did have the idea about inverse trigonometric functions because of the square roots that we're seeing here. But I was thinking, because I was still in just normal A-level maths mode here and trying to avoid further maths techniques, I was kind of thinking, but inverse trigonometric differentiation and integration of inverse trigonometric functions don't really come up on the normal A-level maths, except maybe in challenge problems in your textbook, or possibly if you were given a lot of guidance in an exam, they could come up, but you're not expected to know, for example, that the integral of 1 over the square root of 1 minus x squared is inverse sine x or whatever. You're not expected to know that for normal maths, but you are expected to know that for further maths. Okay, so some of the things that I tried naively, and sometimes you just have to be prepared to try things out. I say this in just about every one of these videos. You've just got to be prepared to give it a shot. Either it works or it doesn't work. If it doesn't work, at least you know. So I tried doing some really crazy things like writing x minus 2 to the half, 3x minus 2 to the half times 1 over x minus 1, x minus 2 times 3x minus 2, and then expressing this, trying to find the partial fraction expansion of this, seeing if that led me anywhere, and then kind of multiplying these back in. Didn't get anywhere with that one. But something that really gave me the motivation that I needed was the following calculation. This was just really, it was desperation. Sometimes this is how it is. Just try things out of sheer desperation, but actually they give you clues about where you need to go. So what I did is I ended up writing this as x minus 1 times the square root of 3x squared minus 8x plus 4, which I then wrote as 1 over the square root of 3, x minus 1, square root of x squared minus 8/3 x plus 4/3, which is equal to 1 over... I was very hopeful at this stage, by the way. This is once I'd realised that you could incorporate further maths techniques. I was getting my hopes up at this stage, but my hopes were dashed, because what I ended up with was x minus 4/3. I completed the square on this thing in here. So what do we get? Minus 16 ninths plus 12 ninths. So this is equal to 1 over square root of 3, x minus 1, square root of x minus 4/3 squared minus 2/3 all squared. So at this stage, what I was hoping for here is that I'd get x minus 1 in here, because then this would be a clear trigonometric substitution. So it would be either inverse cosec or inverse sec. Okay, I can't remember off the top of my head which one, but you can. What I did was calculate this, calculate the derivatives. Okay, I generally speaking don't rely on formula books and things like that. If I need to know a derivative, for me it's important to know how to derive the derivatives of inverse trigonometric functions and things like that, because then I know that if I get really stuck, I can derive them, and it deepens my understanding. Okay, I might go through it in a second, what I'm talking about, but don't rely on the formula book to bail you out all the time. Don't use the formula book. There's some things in the formula book as an excuse for not knowing it, not knowing that formula, and not understanding as well as you can how that formula comes about. Okay, right. So this didn't quite work. If this had been x minus 4/3 or this had been x minus 1, it would have been perfect, right? But it's not. But this kind of convinced me that there was something there. There was going to be a substitution that I could make that would bring this into the right form. Okay, so I did try some really naive kind of substitutions first, because what I tried to do was to try to bring this into a similar kind of form as the parts 2 or part 1. I knew it was going to be very difficult, if not impossible, because the powers don't work here. You don't have the power to the 3 halves and power to the half. But I tried some naive ones, like u equals x minus 1, u equals x minus 2, obviously. And then I thought, okay, maybe I need to try something a bit more complicated. So bearing in mind that the substitutions that we've used in part 1 and part 2 have been substitutions of the form, well, in the first one it was 1 over 1 minus u, right? And then in the next one it was, I can't remember what it was off the top of my head, but I made a couple of substitutions, but one of them was u equals, what was it? 3 over t minus 1. So it led me to believe that a substitution of this kind of form was going to be maybe the direction that I needed to go in. So I tried a few things out, and yeah, sometimes you're just kind of stabbing around in the dark, hoping that something's going to work, until you realize that it's staring you in the face what you need to do. Okay, so as I think I mentioned earlier in the video, if you've got no other ideas about substitution, try one of the substitutions. You can do worse than just try one of the substitutions that you've already made in a previous part, rather than trying to come up with something brand new. Maybe, just maybe, one of the substitutions that you already have is going to work. And guess what? Guess which substitution works? This one, which is the substitution that we used in the first part, staring me in the face all along. So I don't know how long it took me to come up with the realization that this was going to work, or to come up with the idea of actually just trying this. But it took long enough, okay? And sometimes you just see what you need to see, sometimes you just don't, okay? But once I decided to try this, there was something that happened very quickly that made me realize I was onto a winner with this. And it ties back in with something that I've already discussed. So let's have a look. So x minus 1 is going to be equal to, what is it, u over 1 minus u. And then we get x minus 2 is going to be equal to 1 over 1 minus u minus 2, which is 1 minus 2 plus 2u over 1 minus u, which is 2u minus 1 over 1 minus u. And we get that 3x minus 2, so 3x, so 3 over 1 minus u minus 2 equals 3 minus 2 plus 2u over 1 minus u. This was where I realized that this was going to work. Or I was 99% certain that this was going to work. Once I saw these two expressions coming up, I knew this was going to give me exactly what I was after. So you remember what I was saying earlier when I had the expression? It was like x minus 1 square root of x minus 4/3 squared, and so on and so forth. I said if the x minus 1 and the x minus 4/3, if they were the same, then we're good, okay? Because then I've kind of got an inverse trigonometric derivative. That's what we're going to get here, okay? Let's see. So this becomes, again, I equals, because I'm lazy, I equals the integral. So what the limit's going to be when x equals 2, we get u equals a half. Right, okay, so when x is equal to infinity, so rather than doing that, let's do 1 minus u equals 1 over x. So therefore u equals 1 minus 1 over x. So if x is, rather than saying infinity, if x is a really, really, really big number, this is going to get closer and closer to 0. So therefore u is going to get closer to 1 minus 0, which equals 1. So the upper limit is going to be 1. I don't like using infinity in expressions. You can get away with it sometimes at A level. In fact, a lot of the time you can get away with it. And you won't be marked down for it, by the way. Because you're not expected at A level to really have techniques, well-developed techniques of circumventing the issue of the infinite. These are things that you will develop at university, but you're not expected to to have these techniques nailed at this stage. So don't worry about it. 1 over, what is it, x minus 1. So we get, okay, 1 minus u over u times x minus 2 to the half. Don't forget the half. So it's going to be 1 minus u to the half. And I'm going to write it as the square root of 2u minus 1 times the square root of 2u plus 1, 1 minus u to the half. And what do we get? Dx by du is going to be equal to 1 minus u to the minus 2. So that's going to be 1 over 1 minus u squared du. We get all of our cancelling again. Cancel, 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 cancel. And we end up with the integral from a half to 1 of 1 over u times the square root of 4u squared minus 1. And that's exactly what I was hoping for earlier. But it was just a matter of finding the right kind of substitution. Okay, so I didn't know initially, I had no idea, absolutely no idea how to deal with this. It's not a standard problem. It's not a routine problem. There's no set way of going about it. You've just got to pick up, initially it's a few scraps that you've got here and there, a few scraps of information, and you've got to start to try to build on them and take the clues and try to build on these little bits of information that you have. Just try to build on them so that they actually turn into something useful. It's a long process. Okay, problem solving is hard, and there is no way to make it easy, unfortunately. Right, so this is effectively a derivative of a particular trigonometric function or inverse trigonometric function, and it's inverse sec. Okay, so if you don't know the derivative of, you should at least know the general forms. Okay, so I didn't know off the top of my head what the derivative of inverse sec was or inverse cosec, but I've got registered in my mind approximate forms, and I know that this is kind of inverse cosec or inverse sec. I don't necessarily know which one, but I can find out. Okay, so just to give you an idea about what, by the way, I didn't refer to a formula book to figure it out. I actually did the calculation myself because it's good practice. Okay, take these opportunities. Don't be too keen to just look at the answers or grab your formula book or get something. One thing now that people seem to be getting into is Chat GPT and things like that. Just don't do it, because you need to go through the process of problem solving yourself. And if that means that sometimes you've got to, in the middle of a calculation, actually derive a particular derivative yourself, do it, because it's all contributing to your understanding, your overall confidence level. And it's just essential, really. To keep denying yourself these opportunities means that you don't make the progress that you could make. You're not using your time as effectively as you could be. And if you're preparing for a STEP exam, you need to be really maximizing as much as possible the amount that you learn in the time that you have available to you. So we've all got a finite amount of time. You've got to maximize your learning opportunities. And it's not just about getting the answer as quickly as possible. It's about getting the answer in a way that you understand and where you're going to be learning the most about what it is that you're doing. Okay, so just to give you an idea, let's say we've got y equals inverse sec of x over a. Then rearrange this, we get sec y is equal to x over a. I used to be fascinated by differentiation of implicit functions and things like that when I was doing A levels, because it allows you to do so many things. So you can differentiate this now, and you can get sec y tan y dy by dx is equal to 1 over a and you get dy by dx is equal to 1 over a sec y tan y. So you've got sec y is equal to x over a. I'm not going to do the whole calculation, but also you've got the identity tan squared y plus 1 is sec squared y. So therefore tan y is, because we're dealing with positive values here, it's going to be the positive square root of 1 minus sec squared y minus 1. Again, you've got sec squared y. Okay, so following this through, you'll find that the antiderivative of this is inverse sec of 2u between a half and 1. Okay, inverse sec of 2u. So I'll leave you to do this yourself, but this is the idea. I went through this calculation, and it's good to do this, especially when you're not in the exam and you've got the time available to you. Just do it. It's good practice. You're practicing all sorts of things here. You're reminding yourself of trigonometric identities. You're reminding yourself of derivatives of certain trig functions. You're reminding yourself of implicit differentiation, all sorts of things, right? You're getting that extra practice in all of these techniques. And this was, when I was doing A-level maths particularly, this was one of the things that I used to spend a lot of time doing, just deriving these derivatives and deriving formulae and things like that. And without realizing it at the time, I was giving myself all of this extra practice. Okay, so when I was supposedly doing, integration, I might be doing using all of these other techniques from different parts of the course without necessarily even realizing it. So I was revising, because one of the problems that a lot of people have is, because if they treat everything, all of the topics that they do at A-level as separate topics, it just becomes a juggling game for them. Okay, and they find it difficult to keep everything up in the air at the same time, because they think when they're doing this topic, they can't be doing anything else. And when they're doing that topic, they can't be doing anything else. So they do this topic, and then they do that topic, and then they do that topic. And by the time they get to the 5th topic, they've started forgetting stuff with the first topic. And it's just a treadmill. Whereas if you take a much more open-minded approach, where, okay, you're doing this topic, but you're prepared to do things from other topics, and it's almost like you're not seeing separate topics anymore. You're practicing things all the time. You don't have to worry about, okay, today I'm going to do this topic, tomorrow I'm going to do that topic, Wednesday I'm going to do the other topic. You just solve problems. And if you're solving a sufficiently varied range of problems, sufficiently challenging, you find that you're covering all of the topics on a regular basis without even realizing it. Okay, so anyway, back to the problem. So what we get here is inverse sec of 2 minus inverse sec of 1. Okay, so think about the graph of sec. What does it look like? Something like that. Okay, so this is 1 here. So this is x, this is y, this is y equals sec x. So that's going to be equal to 0. What about this one? Well, cos of, I know cos pi by 3, bearing in mind we're aiming for pi by 3, cos pi by 3 is equal to a half. So sec pi by 3 is equal to 2, and therefore pi by 3 is equal to inverse sec of 2. So that's pi by 3. So what do I get? I get pi by 3 minus 0, which is pi by 3. And we're done. Okay, that's the problem over with. So there's a lot to learn from this. As I've said, this is not meant to be a model solution to this problem. I'm really walking you through the process that I had to go through in order to get a solution to this problem. The process that I had to go through is personal to me. It's not necessarily going to be the same for you, But many of the difficulties that I encountered, you will experience during your problem-solving journey in some form or another. Okay, not in exactly the same way that I experienced them, but in your own little way. And you need to develop strategies to deal with these situations. Okay, so it's very important that you allow yourself to go through that problem, that difficult, humbling, frustrating, torturous problem-solving process sufficiently many times. What you feel at the end of it is a sense of relief and a sense of elation, but also the feeling that you know that you've learned something. You might not be able to say exactly what it is that you've learned, but you know that you've come away from that problem wiser than when you started that problem. Okay? Whereas if you just go and look at the answer, you don't learn anything. Okay, so if you found this video useful, please hit the subscribe button. Please hit the like button. If there's anything that you're not clear about in this video, then leave a comment in the comments section. Please share this video and my channel with other people that you think might find it useful if they're preparing for their STEP exams. I'm really trying to reach out to a wider audience, to reach as many people as I can that are preparing for STEP exams and MAT exams and other exams, particularly in relation to applications to university, to high-ranking universities. Because I think that there's a lot of videos online, particularly on YouTube, that cover just the normal A-level maths and to a lesser extent the further maths, but there's not that many videos. There are some, but there are not that many videos that cover the really higher level stuff. So they're the people that I'm trying to get to. So if you know anybody that's preparing for these exams, or even just their normal A-level maths and further maths exams that might find these videos useful, please share them. But show your support for this channel. I can only make these videos if I've got the support for doing it. I don't make any money from making these videos. So it is nice to know that there are people that appreciate my efforts. So without saying any more, I'm going to end this video. That brings us to the end of this problem. Thanks a lot for watching, guys.